Representations of three curves are given below. For each, say whether the representation is explicit, implicit, or parametric, then give representations of each of the other two types of the same curve. Use your calculator to graph the explicit and parametric representations. A, y equals -√4 minus x squared. Okay, so the first thing we'll do is state what kind this is. Because it's solved for y, this is explicit. And so let's get it so that it's an implicit equation where all the x's and y's are mixed together. So let's go ahead and square both sides. Get rid of that square root. The negative goes away and we just get this. And it's starting to look like an equation that I've seen before. Let's add x squared to both sides. Aha, and now finally I recognize it. It's the equation of a circle, centered at the origin, radius 2. Okay, so let's see if we can then come up with a parametric version of that curve. Okay, so let's think about this. Again, there are many different answers. So let's go ahead and draw the circle, but we can't draw the whole circle because this was only part of the circle. That minus sign tells you that the y's are all negative. So instead of being the entire circle, it's actually just the bottom part of the circle. So this is out here at 2, and this is at -2. Okay, so it makes no difference how, like where we started. I'll just go ahead and start it here and then trace along that way. So let's try that for our parametric. X equals and y equals. Okay, so we need to start it at 2, 0. So this isn't something that I said in the class video, but I'll say here, whichever coordinate is not 0, that's the one that has to have the cosine. So I can tell you definitively, this one is supposed to be the cosine, and this one is supposed to be the sine. Because if you plug 0 in for t to get your starting point, plug 0 in right there, you get 0. Sine of 0 is 0. Which is good. That's what I wanted. I want the y to be 0. But cosine of 0 is 1. Okay, I want it to be 2. I can fix that. But you start by making it 1. So how do we make it 2? Well, let's go ahead and put a 2 in front of there. And I guess that means we better put a 2 in front of there to make sure that we get down to -2 at the bottom. So that's our first guess. And then we'll go ahead and plug in t equals pi/2, just like we did in class. So x, we'll write this as a point. Okay, so if we do 2 cosine of pi/2, 2 times 0, 0. So far, so good. Sine of pi/2 is 1. 2 times 1 is 2. The point 0,2 is up there at the top. That's not what we wanted. We wanted 0, -2. So in red, I'll put a negative there, and therefore also a negative in front of that too. So I think that parameterization is good. But we also need to specify the domain for t. And so we're going to start it at 0. If you let it go all the way to 2 pi, then you're going to get this circle to wrap all the way around, which is not what we wanted. We wanted only the bottom half of the circle. So we need to stop this one halfway at pi. Part B, x equals tan t, y equals cosine squared of t. Hint, we're going to use these two identities and encourage you to read the history here. This curve has historical significance, and I'd also encourage you to request at your local library the math book by Cliff Pickover. It is wonderful. Okay, so first thing to do is identify what kind we have. Well, this one's easy to recognize because it's x equals and y equals, so this is currently in parametric form. In order to get it to be in implicit form, we need to somehow come up with an equation that relates the x and the y. So let's see. There's an identity here. Tan squared plus 1 is secant squared. I recognize that. That's one of our Pythagorean identities. I don't know what's going on there, but I see a tan, and I want a tan squared. So how about we square both sides of that guy? So x squared is equal to tan squared, easy enough. And then the next thing that I want to do is try to build a secant squared, because that's also in my identity. Well, I have cosine squared, and I need to get secant squared, but here's the other identity, is that cosine is just the reciprocal of secant. So if I just do 1 over on both sides, then I think we'll have secant squared, an equation with secant squared. So separate equation, 1 over y is definitely 1 over cosine squared, but 1 over cosine squared is just secant squared. So I've got a couple of different pieces here. I've got secant squared there, and then I've got tan squared, which appears here. And apparently if I put a +1 next to the tan squared, I'll make an equation. So that's what we're going to do. This guy, instead of tan squared, we're going to write x squared. Then we're going to stick a +1. Instead of secant squared, we're going to put 1 over y. And according to the identity, these two things are equal. There's a lot of stuff happening in that equation, so make sure you understand what we just did, how to build that thing. We just wrote tan squared plus 1 equals secant squared, but instead of tan squared, we put x squared, and instead of secant squared, 1 over y. So that right there is your implicit version of things. Oh, I just realized that part of the directions say graph the things on your calculator, so you should do that for all three of these, all the different kinds of equations that you're going to play with here. So the last one is going to be the explicit, which means solve for y. So you can solve for y by taking the reciprocal of both sides. And we're done. Okay, and on the next page, e to the x plus e to the y equals 1. So here the x's and y's are all mixed up. So that is called an implicit version. And let's go ahead and solve for y to get the explicit version. Okay, so I'll subtract e to the x from both sides. And then I'll take ln of both sides. ln on the left is just y. ln on the right, sadly, we can't do anything with, because there's no property for ln of one thing minus another thing. And you can't just cancel the ln and the e because this one is in the way. All right, so there's your explicit version of things. And then in terms of the parametric version, there are different choices that you could make. Generally, I make the cheesiest choice possible, which is as follows. I let x equal t, and then I just write down what y is according to the equation right up above. It's ln of 1 minus e to the t. So it's quite cheesy, but it is a perfectly valid parametric form of things. If you are feeling less cheesy, then you could do something different in the answer key. Write down what it says here. It says let x equal ln of t. And then if you do that, plugging into the y equals equation right here, if we put ln of t right up there, then the e and the ln cancel and you just get t. So that means that the y is equal to ln of 1 minus t. Okay, so how did we come up with this ln of t business? I don't know. I didn't write the answer key. I go with the cheesy version. All right, number 2. 3 paths are described below. Find a parameterization of each path. A path that moves back and forth along the diagonal line segment between the point 1, 1 and the point 2, 2. All right, so let's go ahead and draw that. So 1, 1 is here. And then 2, 2 out here. We'll give it some space. And somehow we need something that's going to move back and forth along this path. There, and then back, who knows how many times. So how are we going to do this? Well, we have something that goes round and round a circle, and that's the closest thing that we have to this kind of back and forth motion, is a round and round motion. All right, so here's the basic idea. In order to make something go along that line, first we need to know what that line is. Well, the line that hits those 2 points is definitely y equals x. So as long as you give me two things that are exactly the same, whatever we put here and whatever we put here have to be exactly the same. As long as you do that, you're going to be on the line y equals x. It's just a question of making sure that you're going back and forth along that line, and in particular back and forth between 1, 1 and 2, 2. Okay, so the thing that we have that goes round and round is sine or cosine. It makes no difference which one we pick. I'll choose to put sine of t here and sine of t here. Now, this isn't going to be our final answer, but it's going to get us there. So what's the let's say what's the biggest value that sine of t could ever take? Biggest value it could take is 1, and the same thing down here. So this guy right here at its extreme is going to hit the point 1, 1. Those are the biggest x and y can be. And what's the smallest that x and y can be? What's the smallest value that sine of t could ever take? Well, it could get to -1, and the same thing here. So this guy is also going to get down to -1, which isn't what we want, but it's going to be equal, y equals x the whole time. And so in fact, what we've written down is a parameterization for this part of the line between 1, 1 and -1, -1. And it's just going to bounce back and forth, back and forth. So all we need to do is somehow like shift and stretch and shrink to try to make it so that this part of the line right here ends up moving up to where we want it to. Okay, so that was attempt number 1. Here's our final attempt. X equals y equals. Okay, let's see. I guess we need to make sure that we have a middle at 1.5. And we're going to go up and down the same amount from each one. So let's do a 1.5 plus, both of them. And then how far up and down do we need to go from 1.5 to get to 2? We need to go a half that way and a half that way. So that half is the amplitude, 1/2 sine t. Okay, so I do want to do this one on the calculator just because I think it's so darn cool that we can control these equations as precisely as we are. So 1.5 plus half sine of t, and then exactly the same thing up here. Okay, let's think about the window. So let's make this thing go back and forth. Yeah, this is fine actually. This will make it go back and forth 3 times because that's 6 pi altogether. Step is fine. 0 to 3. Oops. 0 to 3 is good on both. Okay, so now I'm actually losing the ability to see it because it's tracing over itself. So if we hit this guy at the left, enter, enter, the one that looks like a key is what we want. And lo and behold, we've got this thing just bouncing back and forth between 1, 1 and 2, 2. And so you can imagine, you know, with just equations as simple as this, they're simple to us now. You know, you've got kind of the rudiments of a basic video game. You can make motion, and video games are based on motion. And so, you know, like taking these ideas and just continuing to push with them, I think you can start to think about how video games were created back in the day. Okay, part B, a path that moves clockwise around the unit circle, starting at -1, 0 when t is 0. Okay, lots of answers to this one. We need to make sure it starts at -1, 0. So because the 1 is in the x, that's where the cosine has to go. Put the sign over here. If t is equal to 0, and you plug 0 in for the t's in these two equations, cosine of 0 is 1, but I need it to be -1. And then the only other thing we need to do is make sure that we go clockwise. So for example, if you plug in pi over 2 into the first thing, so cosine of pi over 2 is 0, negative 0 is still 0. Sine of pi over 2 is 1, so is this going the correct way? I don't know, let's draw it. So this one started at minus 1, 0, and we want it to go clockwise. So I want it to go up to there, which is at 0, 1, which is exactly what it went to. So I think we're good. Finally, part C, the path that moves counterclockwise around the circle of radius 2, centered at 1, 4. All right, so we'll go ahead and draw a picture here. So we need to be centered at 1, 4. I'm going to draw my picture over here so I have some more space. Okay, so centered at 1, 1, 2, 3, 4. There, and the radius is supposed to be 2, so that means it gets out to there, and there, there, and there. Okay, so we want that circle, and we want it to be counterclockwise, so this direction here. Okay, so how are we going to get that circle to go up there? Well, normally it's just x equals and y equals, and here it doesn't say anything about a starting point, so I'll just randomly put sine up here and cosine here. But how do I make it so that it has a radius of 2? Well, we saw that in the problem at the, up here at the top. It's part A. We made this thing go, for example, was it that one? Maybe it's not the example I'm thinking, but we made this go half in either direction by putting a half in front of the sine and cosine. So we're just going to make this one go out by 2 in both directions. So that'll take care of my radius. And we need the center to be at 1, 4 instead of 0, 0. Okay, so what does that mean? Well, it means that instead of tracing out so like right now we've got the circle centered at the origin. But what we need to do is move this center point 1 unit to the right and 4 units up. That is to say, you need to make x 1 bigger than it was, and you need to make y 4 bigger than it was. And that's true for every point, right? Like this point here on the extreme right corresponds to this guy as long as you go 1 to the right and 4 up. So how do you make x 1 bigger? You add 1. And how do you make y 4 bigger? You add 4. And after this third test, when we talk about conic sections, we will see these kinds of equations, but hopefully we're kind of starting to get the sense that in order to make a center that's not the origin, you just add that center right out here, and that number right in front there is the radius.